Okay, let's get started. So thanks everyone for coming to class. I know that there's been a, request to cancel class today. And yeah, it kind of is tough, right? This air quality is not the best. And it's tough for people here. It's even, there's a lot of people in the rest of California that have been really, really affected. And it just seems that everyone is going through a bit of a tough situation. So it's great that you are in class. I'm happy to be here, and hopefully, given that we have a little bit of a smaller group today, we can take a little bit more questions or make it more interactive. So feel free to come closer to the front if you would like to do that. Okay, so for today, the plan is really to go back and revisit least squares, talk a little bit more about some of the details of the algorithm, and then we'll go a little bit more into when and how the least squares algorithm can be applied. And we're talking about it as one algorithm, but this is something that you will see coming up in many different shapes and forms, under many different names and guises as you go through your time at Berkeley, not just at Berkeley, but through your career as an engineer. It's something that's so fundamental that'll keep coming up over and over again. And today we're going to do kind of a historical perspective on least squares, going back from maybe one of the first times it was applied to much more modern applications. So we'll go over two examples, one very traditional and ancient in some sense, and another that's much more modern. Other thing, just a reminder, I have office hours today after class. I will also have an extra office hour tomorrow, 10 to 11 a.m. This is going to be an office hour specifically focused on catch-up. And so I'll be prioritizing questions from Module 1 and Module 2, as well as study strategies. So if you feel like you need a little bit of extra boost, have some extra questions from previous parts of the class, from Module 1 and Module 2, feel free to come by. Everyone is welcome. And if you want details, go check out the Piazza post about this. Okay, so we're here. Last time, we started off the lecture by talking about trilateration, right? And trilateration is basically the foundation for the locationing example, that is the motivating example for the lab in this module, as well as for us trying to understand least squares. But I wanted to point out something about the trilateration setup that we had last time. So remember, we have these three beacons at these three locations, A, B, and C, and we know somehow the distances D1, D2, and D3. And we started out by thinking, well, what if there's some kind of noise or there's some kind of error in our distance measurements D1, D2, and D3, right? What if we don't get these nice these nice circles that all intersect through the same point? What if maybe they don't intersect at all? What if instead of intersecting at a point, they intersect in a region? And how can we deal with this? And in order to deal with this, something that many of you suggested was, try and make more measurements, or try to somehow split the difference and find a point that minimizes the error on each of these measurements. So what we wanted to think about there was, when we have these errors, how can we improve the estimate? The trilateration algorithm is something that works perfectly in the case that we have exactly accurate measurements. D1, D2, and D3 are all perfect. And so what we had in this trilateration algorithm is the following, right? In the two-dimensional case, we had the following set of equations that we wanted to solve. We had, I'll just write it out here, 2 times A minus B transpose A minus C transpose times X d3 square minus d1 square plus a square minus c square. Right? So I can get rid of this piece of paper. So this was the set of equations we got from trilateration. And when we have a system of equations and we want to solve it, we do the one thing that we know how to do, which is Gaussian elimination, or in the case, for example, that we know that the matrix is invertible, we could just find x by inverting this matrix, right? If we call this matrix matrix A, we can just find x by inverting A, right? We saw that in Module 1. Everyone's comfortable with that? But what do we know about the systems of linear equations? Do they always have a unique solution? Do they always have some solution? Not necessarily, right? We saw all these conditions that connected the invertibility of a matrix to different properties of the matrix, such as the linear independence of the columns, or whether or not you get a row of zeros when you do Gaussian elimination. So here, what happens if A is not invertible? Right? And is there a case that that will actually happen? So what happens if you have the following setup? Is that if your three beacons, this is A, B, and C. What happens if your three beacons that you're measuring your distances from are all collinear? They're all on the same line. What happens to this matrix A? Just, can you take a minute and see what happens? Feel free to talk to people if you want. Right. Is there some kind of linear dependence in the rows, columns, something? Can you come up with an example where here you can get, can you draw a picture here or augment this picture to show how you might end up at a location so that you won't be able to precisely figure out where you are? Think about it. Just play with the example just a little bit. How many people think they can draw a point such that if I tell you that, your distance d1, d2, d3, you might not be able to precisely pinpoint where you are? Yeah, 1, 2, 3, some people. Okay, anyone want to share their idea? Yeah? Great. What was the suggestion? Take a point that's not on the line. So if I take, let's say I take this point here. Let's say I'm at this point. And I measure distance. Let's say I measure distances d1, d2, and d3. Right? I can take the point here that's perfectly the reflection. And what are the distances from these three, what are these three distances for this reflected point going to be over here? They're going to be exactly the same, right? This is exactly going to be d3, d2, d1. So if I get these three measurements, d1, d2, d3, I cannot disambiguate between whether I'm here or I'm here. And how do we see this from this measurement matrix A? Remember in the first module, right? We always realize that whether or not we will have a unique solution does not depend on the data we measure. It depends on how we take the measurement, right? And we're seeing this again here because this matrix A, does it depend on the distances? It only depends on the locations of the beacons. And so if these locations, so now if I have A, B, and C in one line, what is A minus B in terms of A minus C? It's just a scaling, right? When these three things are collinear, A minus B and A minus C are exactly just multiples of each other. One is in the span of the other. And so trilateration doesn't work if your beacons are collinear. Right? So it's something to keep in mind. What we're seeing here is that, well, things might not always work. But is this a problem for us? Who gets to choose where the beacons are going to be put? We do, right? So we get to choose to not put them in a line. And we can make our measurement matrix in a way that we can actually invert it. But this is something that you need to keep in mind when you're designing things. So now that we're seeing this, do you think some such problem could also show up if we were running a least squares algorithm? Are we always guaranteed to have a least squares solution? Right? Maybe, maybe not. It's going to depend on our measurement matrix. And this is what I want to try and look into a little bit for the first part of the lecture. So let's now move to thinking about least squares. And here, remember, now instead of having measurements exactly from the number of beacons we require, we have an overdetermined system, right? So we have this tall matrix A with these columns A1 all the way up to AN. And we have some x that is unknown. And this is maybe approximately equal to whatever data that we're measuring. And let's say A has dimensions m by n, and m is much larger than n. So m is the number of rows, n is the number of columns. You have a lot more measurements than you do have variables. And B is, again, an m by 1 vector. And x is n by 1. So the first thing to notice about A in this case is A is not a square matrix, right? That's the kind of point of a least squares algorithm. Since A is not a square matrix, can you tell me if A is invertible? Invertibility is only something we've talked about for square matrices, right? If it's not square, you cannot invert it. So trying to figure out whether A is invertible isn't even really the right question to ask. Like, clearly A is not invertible because it's not a square matrix. But can we use some of the things we've been using? Can you use Gaussian elimination on a matrix that's not square? Yeah, you can use Gaussian elimination on a matrix that's not square, right? So what would happen if we have a matrix like this? Let's say we have something simple. Okay, I need to appoint someone in like the one person in the front row and one person in the back row. If you accidentally cannot see the paper, it is that person's responsibility to tell me that you cannot see the paper. So someone at the back, can you volunteer to do this job? Okay. Someone in the front, can you volunteer to do this job? Okay, great. Your guys' job is if I accidentally do not show the paper, tell me. Thank you. Here. So, if you run Gaussian elimination on this, what do you get? Can you quickly do it out? Take a minute. It should take you a minute just to do it. Quick. I'm just going to get 2. Right? When I run Gaussian elimination on this, what do I get? I get this guy, right? I get this row of zeros that's not equal to 0. So what does this tell me? That I don't have a solution, right? We know this from Gaussian elimination. So we know that, in what case, let's say I have now many, many more equations than I have unknowns. Am I guaranteed to get a row of zeros not equal to a 0 all the time? Yeah? I see no's shaking their head, right? What if, that's good, that's correct, if B is in the span of A? If B can be expressed as a linear combination of the columns of A, will Gaussian elimination give me a solution? It will, right? So if B is in the column span of A, I will actually get this kind of precise solution that I need. So the case when you want to use a least squares type algorithm is in fact the case where, well, not really, might not, but you will have a solution. The case of interest is when B does not belong to the span of A. Right? And this is the case where we want to try and use a least squares type algorithm. And so if B does not belong to the span of A, what did we do last time, right? I'm just going to quickly review it. I know that I have, if B does not belong to the span of A, is there going to exist an X for which I can write AX exactly equal to B? No, this isn't going to happen, right? So what I'm going to do instead is I'm going to write AX is equal to some B hat plus some error vector. So this guy is equal to B. And the way I'm going to think about it is let's say I have the column span of A. I have my vector B. Let's say there's some vector B hat in the column span, and B hat plus E is going to give me exactly the B that I'm interested in, right? This is how we set it up last time. And then we said, well, we want to minimize the length of E, right? E is our error. We want to minimize error. And one way of minimizing error is to think about the length of the error vector, right? Just intuitively, if you have a vector here and you have a vector here, the closer the vectors get together, the better one approximates the other, and also the smaller the error between them, right? Yeah?
So you said AX equals to B couldn't happen, so should it be AX equals B hat there, and then B hat plus B equals B?
So that's exactly what I meant. Good point. So what I want to say is that AX is exactly equal to B, but what we're measuring is this other B. So AX will be this B. B hat plus E will give me B. So really what I want is I want to find essentially an X hat. I want to find, ideally, what I'm given is what I want to try to solve. I want to solve, let me write it here. but I can't. There's no exact solution because B is not in the column span of A. Yeah, good question. So instead of finding exactly this x, I'm going to try and estimate a good x. I'm going to find an x hat such that this is going to be true. So I'm going to write basically A x hat is equal to B hat, where x hat is an estimate of the true x, and B hat is an approximation for B in the span of A. And you'll see this notation hat showing up. And you know, when we usually, this notation hat is something that is approximating the other vector. It's either approximating or estimating. And you'll see, depending on the exact context, whether you're estimating or approximating might change, but that's what hat means. Okay, so we want to minimize this E. And so we, let's say, can also think about minimizing the square, again, of the length, because that's easier. And so what we really want is we want to have, we know that if I wanted to minimize this error, what kind of B hat do I need to compute, right? We looked at projections and we know that the minimum error is going to come when I project my vector B into or onto the span of A, right? So I want to compute exactly what this projection is. And so what I want basically is I want B minus B hat, which is equal to this E, to be orthogonal to the span of A. Right? And what does this mean? This means if it's orthogonal to the span of A, it means that it is orthogonal to every vector in the span of A. And so I can write this now mathematically using inner products, right? I can say B minus B hat inner product with A, 1 is equal to 0, right? A1 is my first column of A. Right? A1 is clearly in the span of A. So that's 1. What's the next equation I can write? It's kind of obvious. Great. And what's the last equation I can write? Is AN, right? So I have this now written out as these inner products in this mathematical form. But I want to now transform this into a matrix vector equation because matrices are easy to manipulate and we've been spending all this time building up all this work to get to being able to manipulate these things. So this I can rewrite as the product of this vector transposed with A1, right? So I can write B minus B hat transpose times A1 is equal to 0. And I can also write it as A1 transpose B minus B hat equal to 0. Everyone see that? So, what we have now is we can actually write this out as a matrix vector product, right? By taking and stacking all of these. So I have a bunch of rows here. I have A1 transpose, A2 transpose, and I have B minus B hat. So I can rewrite this as A1 transpose B is equal to A1 transpose B hat. And I have n equations like this. AN transpose B is equal to AN transpose B hat. And now if I have a bunch of rows, how can I stack these to make a matrix? I can make these rows in this kind of stack. This will actually be pretty short. Any questions on how we got to here? Is everyone with me? Yes? So now if you look at this matrix, how is this related to our original matrix A? Anyone? These are the column vectors of A. And what we have here are A is becoming, what was a column vector has become a row vector, right? So this matrix is A transpose. Does everyone see that? The first column is the first row, the second column is the second row, the last column is the last row. And what we have here, what do we have here? Also A transpose. So I can write A transpose B is equal to A transpose B hat. Yeah, question?
Go back to your inner product, B minus B hat A.
Mm-hmm.
Would you mind explaining how you got from that to the transpose?
How I got from what, this to this transpose?
No, the first phrase is that B minus B hat A1. How did you get to that transpose there?
That's the definition of inner product. So, just by definition. Inner product is just the dot product of the vectors. So you take the first vector, you transpose it, and you get the second, and multiply by the second vector. It's not, there's no flipping the rows and the columns. It's just basically taking one as a row vector and the other as a column vector and doing matrix-matrix multiplication. And because inner product is commutative, it doesn't matter which one you transpose. So if you just look at the rules of matrix multiplication, you should be able to derive that inner product of A and B is the same as inner product of B and A. Just write it out using the sum. Yeah? Okay. Everyone with me till here? Okay, great. So now what you have is, we're almost done, right? Remember, what do we want to find now? We did some equations, we did some algebra, we did some manipulation. How do you come back to where we want it to be? What did we want to find? We wanted to find x hat, right? We wanted to find this estimate for x. What here is related to x hat? This is related to the very nice question that was asked. Right? We have B hat related to X hat in this nice way. So can I rewrite this as A transpose times A times X hat? This guy is coming from here. Does everyone see that? Okay, So now we have something interesting. We have A transpose B is equal to A transpose A times x hat. And we want to find x hat. So what do you feel like doing to find x hat? I have this guy times x hat is something. Let's remember here, what are the knowns and what are the unknowns? Yeah, question? No. Oh, yeah, go for it. Right. To find x hat, we have to multiply both sides by the inverse of A transpose A. Let's do a quick check. What are the dimensions of A transpose A? What is A transpose? How many rows are there in A transpose? N. And how many columns? N times M, right? And what are the dimensions of A? M times N. So what are the dimensions of A transpose A? N times N. So this guy, thankfully, is a square matrix, which means that we can actually invert it. So exactly what we want to do. So what we're going to write is we're going to write x hat is therefore equal to A transpose A inverse times A transpose times B. Now, when we draw this like this, when we write this like this with A transpose A and this inverse sign on top, do you see, can we take the inverse inside the bracket? Not really, right? Not in the same way that we always do. Because, does A inverse exist? Can we write this as A transpose inverse times A inverse? No, because A inverse doesn't exist. It's not a square matrix. So be very, very careful about your internal temptation to, switch the inverses and the transposes. The order actually matters here because matrix multiplication is not commutative. So keep this in mind. So we have this, and now if I wanted to use this to find B hat, which is my projection of B, how could I write this? I know B hat is A times X hat, so this gives me A times A transpose A inverse times A transpose times B. And this is basically the least squares estimate development. And this, I would say, is the estimate of X. And this is your estimate or projection of B on the span of A. Yeah, question? How do we know that A transpose A is invertible? Excellent question, right? How do we know that A transpose A is invertible? Is A transpose A invertible? Yes, maybe, sometimes, maybe not. Do we know this? Is it always invertible? Yeah.
But isn't the columns of A or linearly independent?
It seems to be related to the columns of A, right? So can we actually formalize this and prove this and think about a way of making this concrete? Because exactly what you should be thinking is what you are thinking, which is great. I just said, let's take an inverse. Boom, done. But what if that inverse doesn't exist? What if A transpose A, we checked that it was square, but did we check that it has an inverse? We didn't. So how do we know that A transpose A is invertible? This is exactly what we're going to talk about next. And so we're going to write a caveat here, which is that this is the least squares formula. If A transpose A is invertible. Great. Okay? So, we are now off on an investigation invertibility of A transpose A. Okay, we know A transpose A belongs to R n by n. We already just computed its dimensions. So what do we know about invertibility? How can we check if something is invertible or not? Right? What are the ways that we already know? We already talked about columns, right? We talked about linear independence of columns. So if A is square, we know that A is invertible when the columns of A are linearly independent. So if we look at the columns of A transpose A and they're linearly independent, then we can say A transpose A, the product matrix, is invertible. But can we say something about the invertibility of A transpose A, not in terms of A transpose A, the product matrix, but just in terms of the matrix A itself? Can we think about how to say something about this product matrix just using A? And that's what we're going to do, and we're going to actually use the connection between invertibility and null spaces. What do we know about invertibility and null spaces? Do we know anything about invertibility and null spaces? Yeah? Great. What he said was if the null space contains something that is not just zero, so if the null space is non-trivial, then the matrix is not invertible. Right? So we want to see if the null space contains something non-zero or not. And we're going to actually do something that's kind of nice, which is we're going to connect the null spaces of these matrices. And we're going to prove a theorem that says the null space of A transpose A is equal to the null space of A. And we know that if A has a non-trivial null space, then the columns of A are linearly dependent. These two things are the same thing, right? We know this from Module 1. So that means that we can check the invertibility of A transpose A using just the columns and the linear independence or dependence of the matrix A. So how would we go about proving a theorem like this? Right? There's two parts to a proof like this. So let's say we want to show first if a vector V belongs to the null space of A, then V belongs to the null space of A transpose A. If I show this, are we done? Is this enough to prove the theorem that I want to prove? Just the fact that I wrote a 1 here indicates the answer, right? So what is the other thing that I have to prove this theorem? Someone at the back. Yeah? Red jacket, yeah. The other direction, right? I have to say, if some W belongs to null space of A transpose A, then W also belongs to null space of A. If I can prove these two statements, then clearly these two spaces must be the same, because any element in one is in the other, and vice versa. Right? If I just prove the first statement, well, they might not be equal because one of them might still have extra stuff. So how do we prove this? Let's say, how do we prove something like 1? So let's start. Let's say V belongs to the null space of A. And what does this mean? Well, we're given one thing. Let's just write it out because we only know one thing. A times V is equal to 0. And now if I want to prove that this also belongs to the null space of A transpose A, what do I want to do? I want to show that if I take A transpose A and multiply it by V, I also get 0. Right? So how do I show that? How can I get A transpose times A times V? What's the only equation I have? I only have one equation, and I want to somehow get an A transpose A. What do I do? Yeah? Multiply by A transpose. So I get A transpose A times V equal to A transpose times 0, which is equal to 0. So I have A transpose A times V equal to 0, which means that V must belong to the null space of A transpose A. Right? What about the second direction? What if W belongs to the null space of A transpose A? Can you prove this in some kind of similar style? So, take a minute, digest what happened in the first part. If you're confused, talk to your neighbor or ask a question and see how you can show the second statement. How can you show the second part that we need to do to actually prove the theorem? Feel free to talk. Yeah? The purpose of that is to actually show that every element in the first subspace is an element of the second, and every element of the second is in the first. Otherwise, you might have unequal things. We can talk more about this after class or in office hours. Figure out a strategy with your neighbor to see if you can actually prove the second part. How many people think they have a strategy? Maybe, sort of. Okay. Good. Does anyone want to share their strategy? It's a bit of a tricky proof. I'm not expecting everyone to be able to figure this out. It's something slightly new and different from what we've done here. So let's write down the one thing we know, right? We know that W belongs to A transpose A. Whenever you're doing a proof and you don't know how to start, what do? You write down all the things you know. What is the one thing you know in this case? You know that A transpose times A times W is equal to 0, right? Okay. And now I want to somehow use this to show that AW is equal to 0. Except, what is the issue? You wish you could just multiply by the inverse of A transpose, right? You're please. But you can't. So, can we try to do something else? Yeah? Good idea. That's a very great idea to try. The suggestion was, can you multiply by inverse of A transpose A? That's exactly the idea that I would think to try first after this. This is the invertible matrix, but when we multiply by inverse of A transpose A, what we're going to get is just an identity matrix here. And we're going to lose the A part of it as well. Right? The inverse will kill A transpose and A. We somehow want to kill the A transpose part, but keep the A part. So just multiplying by the inverse doesn't actually quite work. The trick that we're going to do is actually we're going to say multiply by W transpose. What we're going to do is we're going to say take W transpose times A transpose times A times W. And what is this equal to? This is W transpose times 0, which is equal to 0. So now I have this. And this is where I'm going to do a little bit of a small aside on transposes. So let's pause on this, and we'll do an aside transpose. If I have A times B whole transpose, how does this connect to A transpose and B transpose? This is actually equal to B transpose A transpose. So you transpose both the matrices, but you also flip the order of the multiplication. Think about why you have to do this. Let's say A is m by n and B is n by m. Right? You can multiply these guys because the number of columns here matches the number of rows here. But if I take A transpose, this is n by m, and B transpose, this is m by n. Can I multiply them directly? It's like the dimensions are weird, right? If I multiply them directly, am I going to get an m by m matrix? If I multiply A transpose B transpose, I'm going to get an n by n matrix, right? But if I multiply B transpose A transpose, what dimensions am I going to get? Exactly. Right? So it's worth going and like writing out and doing some examples. Let's do one quick example here. So if I have, for example, 0, 1, 2, 0, let's say times something simple, 1, 1. I take this and I transpose it. This is going to give me, let's say, 1, 1 times 0, 2, 1, 0. And to verify that this is correct, what is this going to give me? This gives me basically 0 times 1, 1 is 1. This gives me 2 transpose. And this multiplication gives me 1. And then that gives me 2. And so here's a way of checking that what I told you is actually correct. You know, take another example, do it on your own. Like, for example, take 0, 1, 2, 0 times 1, 2, 3, 4. Transpose. You know, you'll see that this is actually equal to 1, 2, 3, 4 transpose times 0, 1, 2, 0 transpose. Okay? So now that we have that, we have this aside on transposes. What does, if I have a vector, if I have x transpose times x, what does this remind me of? X transpose times x, what is this of x? Is it related to the norm of x? It's equal to the norm of x, right? X transpose times x is equal to the norm squared of x. That's the definition of norm, right? And so, what is this guy equal to? This guy is equal to the norm of a w squared. Do you see that? X, think of this as a vector x, or this is a vector a, w is a vector x. I transpose it to get x transpose. The transpose flips the order, so I get w transpose a transpose. And this, therefore, is equal to just the norm squared of this vector. But if I have a vector of length 0, what is the only vector that can have length 0? The 0 vector, right? So this means that AW must be equal to 0. And what does this therefore imply? That W must be in the null space of A. Right? We did like a non-trivial step here. We did two things. One, we had to notice how transposes behaved, and second, we used the fact that if a vector has 0 length, it must be the 0 vector. Thank you. Okay, you're also appointed as a deputy. Everyone with me? That's the definition of norm. Yeah. Okay, good. So what this says is now we can have basically right? How did we start here? We ended up here with this investigation because we wanted to say, well, when can we actually use the least squares estimate, right? You had the great question of, well, is A transpose A invertible? And now what we can see is that, well, if the columns of A are linearly independent, then A transpose A will have an inverse. Right? If there's a non-trivial null space, then the columns are linearly dependent, which means you cannot invert A transpose A. Which means that basically you have a bunch of redundant measurements, and you need to take more measurements. You need to take enough measurements so that the columns of A become linearly independent. And again, this is something that is in your control. It's like saying, I want to make sure that my beacons are not in a straight line, right? You get to choose where you put your beacons. You get to choose what kind of light you're going to shine onto your image to get your projection, to get your measurements. You get to design these things. Okay, so now that we're here in the last part of class, I wanted to actually do some very fun stuff. And I want to talk about different interpretations of least squares. Yeah, just for a second. Yes, question.
Yeah, for the last part, when we tried to find the estimate of x, technically we said b and b hat are equal, so we eliminate the...
We did not say b and b hat are equal. We said b hat is an estimate of b. B hat lies in the column span of A. B does not necessarily apply.
We are not saying that there is no error.
We are not saying that there is no error. We're saying that when we apply the least squares estimate, we're going to try and minimize the error. We're going to try and make it as small as possible. But we might not be able to make it 0. In the case where A itself is a square matrix and you have a perfect solution, in that case, you will actually get a perfect answer. So in the case, let's look at this, right? If A is actually square and invertible, it's worth working this out to see what you get. And what you'll see is that this will actually end up being A inverse times B when the case is when A is actually square and invertible. Okay. So, back to least squares, what we want to think about is different techniques. Like, this is a tool, it's a powerful tool, and we're going to use it. So the first application we've seen is it's basically an approximate solution to systems of linear equations, right? If we want to find an x hat such that ax hat is close to b, we want to find an x such that ax is approximately b. This is a technique that we can use in the event that we cannot find a precise solution. The second thing we've seen is, let's say we have some vector b, and we want to find a b hat that's somewhere in this subspace given by the span of A. How do we find a vector in the span of A that's close to B, right? So we've seen a projection interpretation. We wanted to find an x hat, or find an x, which is the argmin. This is a new notation. Right? X is called the argument. Find the argument x that minimizes this expression. That is what this argmin means. So this is the second projection interpretation that we've seen. But now I want to talk about a third application that is more machine learning, prediction, regression, or curve fitting. Which is, can I use least squares to approximate different functions, or to try and develop models that will help me predict what will happen at times when I actually don't have the data? So the plot I showed you about the correlation between fake news consumption and voting outcomes, right? This is an example of somewhere where getting that line to fit, getting that regression, is something that you can do using least squares. And for the rest of the class, that's actually exactly what I want to do. So let's consider a simple example of the financial stock market. How many people in this room would like to be able to predict how the stock market is going to behave? Right? You can make a lot of money trying to do this. You could also go into academia. But some people choose to not do that. Anyway, let's say we have some stock, we want to try and predict, how the stock of a certain company is going to behave. Maybe, it just had an IPO, you've been observing how it's been doing, and you want to predict how things are going to go. And so let's say you do this and you collect some data. Okay, so can you read this at the back? Yeah? Okay. So I'm just going to show you some data here. I'm just loading stuff. I'm just defining a function called least squares. And now I'm actually going to load stock prices for this large tech company that none of us have ever heard of. And let's plot it. And what you have here, let's say IPO happened here. And this is the stock price every month after IPO. And you've been collecting this data, and now you want to try to decide, well, if you buy the stock now and you hold it for 1 month, 2 months, 3 months, how much would you make if you sold it in X number of months, right? You want to be able to predict the price after a certain amount of time. Would you use the strategy that we are going to use right now to actually make financial decisions? The answer is no. This is going to be a very, very simple strategy, but it forms the basis of how prediction will work in the real markets. So you have this, and you can say, well, can I try and understand the trend that we see here? And if you had to guess the trend here, what would you guess? It's a linear trend, right? It's going up. So let's try and think about that. So we have the stock price Y, and we can write it as Y is equal to, let's say, some alpha times X, which is the month after IPO. This is the price, plus maybe some constant beta, right? This is going to be the slope. And this is the intercept. So what is known here? Known, the stuff that's known to me, are the stock prices. So I know xi, yi at different months, right? I have multiple data points xi, yi. What is unknown is alpha, beta. And I have this set of equations. I have y1 is equal to alpha x1 plus beta. y2 is equal to alpha x2 plus beta. Let's say I have n data points. Yn is equal to alpha xn plus beta. Can I write this now as a matrix vector equation? To do that, first, what is the vector of my unknowns here? Can someone shout it out? Alpha, beta, right? What are the unknowns? I'm going to write the vector of my unknowns as alpha, beta, right? So I have an alpha, beta here. And I want to fill in some kind of matrix here. So what do I have from my first equation? I have alpha times x1 plus beta times 1 is equal to y1. So how can I fill out the first row of my measurement matrix? I have alpha times x1 plus 1 times beta 1, or 1 times beta, is equal to y1. The second row is x2, y2, all the way up to xn, 1, yn. So the number of measurements, the number of months that I've been measuring the stock price is actually the number of rows in my matrix. And because I'm using a linear fit, I'm fitting a line, how many unknown parameters are there in the definition of a line? 2, right? The slope and the intercept. So we have these 2 unknowns. So now if we were to try and do this actually on our data, so we have this here, and so what we're going to do is we're going to put this data, we're going to make this vector of, so here what we're doing is we're going to make the A matrix and make the B vector, which is, this is our measurement points, this is our data. And then we're going to call the least squares algorithm, right? And now I'm going to say, well, let me take my estimate of the slope and my estimate of the intercept and figure out what the model is. And I can now plot this line that is actually the fit through the data. Right? I just used the least squares algorithm to compute the parameters of the line. But now, like here, I have data for 61 months after IPO. What if I wanted to predict what would happen for, let's say, the following months, right? What intuitively are you going to want to do? What are you going to plug into the y is equal to alpha x plus beta? Now you have estimates for alpha and beta. If I want to predict what's going to happen in the 62nd month, what is the value of x I'm going to plug in? 62, right? And so that's exactly what I can do. And now I can generate a prediction. And now I can fill in predicted values. And this is basically what, a lot of machine learning algorithms are built on. What the green dots are called is what is called training data. The blue dots are your prediction. You have some training. You're building a model. The red line is your model. You're training the model based on your data. And then you're using your model to predict something. Sometimes you have a notion of test data. You'll see this a little bit in your homework, where you have some data that you will test and you will evaluate how good your model does. Just wait for a second. I want to get through something before the end of class. Yeah. So what we're trying to do is we're trying to learn and summarize the information from all of these data points. Right? We could have said, well, every time, let's carry around 62 data points. And every time we do this computation. But what this model is doing, what least squares is allowing you to do, is it's allowing you to summarize this information in a compact format that then you can use for prediction later on. So machine learning, when we talk about it, there's multiple aspects to what this algorithm is doing. One is it's allowing you to predict. But second, it's serving as a summary, a compact representation for everything you've seen so far. So now that we have this very, current and possibly applied application, I wanted to go into another example that is actually quite historical. And if you're interested in learning more about any of these kinds of things, this is basically setting up a foundation for you to take now 16B next semester, then go into 70, classes like 126, 127 will go into a lot more detail on how to build these kind of models, how to do these kinds of predictions, and learn from them. But the last application I want to do is I actually want to talk about a curve fitting application. And this actually comes from the origin of least squares. So least squares is an algorithm that many stories say was developed not recently at all, but was developed back in the 1800s. And it was developed by someone that has come up many, many times in this class before. You've heard the name many times before. Gauss. He used it in the context of actually making an astronomical prediction. And so one of the things that people were very interested back in the 1800s is trying to understand planetary motion and trying to understand how to understand what is happening, or trying to understand what's happening in the skies. And so there was a planet at the time called Ceres. And this was a planet that was being observed by this astronomer called Piazzi. And he would make these observations of the planet, actually. Oops. So for example, here's a map. You can see this. And these arrows are showing the positions that he measured in the sky on January 2nd, January 22nd, and February 11th, as it's moving. And he actually made 42 observations over the course of some time in trying to understand these motions. But then suddenly, he stopped being able to make observations. He couldn't find the planet in the sky because of various occlusions and, light coming in, polluting the telescope from other planets and stars. And there was a patch where he could not see where the planet was. The question is, can you now figure out the trajectory of the planet and predict where it's going to emerge after, this period of unobservability has passed. And this actually became somewhat of a competition among the mathematicians at the time. People proposed various solutions. But the prediction that ended up being most accurate was actually the prediction that came from Gauss. And what he used was a technique that is thought to be quite similar to least squares. There's different versions of the historical story on this, but largely, many people credit this as the first time, or one of the first times that least squares was actually used. And what he used to do this prediction is Kepler's law. And what does Kepler's law say? Kepler's first law, which is from the late 1500s, early 1600s, I believe, it says basically that planets have elliptical orbits. They have elliptical orbits around the sun, and the sun is one of the foci of the ellipse, right? And what Gauss did was he used this law to actually have an equation for the path of the ellipse, or for the path of the planet, and therefore be able to predict where the planet was going to be. And so what he had, if we were to think about a 2D model, were these pairs of points, x1, y1, x2, y2, xn, yn. I believe at the time he had 42 points, or 42 observations from Piazzi. And what he said was, well, can I now use these measurements or these feature vectors? Can I develop feature vectors that will help me? Well, he didn't use the word feature vectors, but that will help me then predict where the planet is going to be. And because he knew that it was going to be an ellipse, he could write out the following equation: ax squared plus bxy plus cy squared plus dx plus ey equal to 1. Right? This is the equation for a general ellipse. And again here, can we think about what are the things that Gauss knew when he was writing this? He wasn't writing exactly this 2D equation, but he was doing something quite similar. What are the data points that we have? The x's and the y's, right? What are the unknowns? Right? These guys are the unknowns. And now if I want to write this out again as a matrix vector equation, how can I write this? I'm going to write out my unknowns. A, B, C, D, E. So what is the coefficient of A? What is the first equation I have that involves A? I have this data point. I have this equation. What is the first row? x1 squared, x1, y1, y1 squared, x1, y1 is equal to 1. And then the second row is given by the second data point. All the way up to xn squared, xn, yn, yn squared, xn, yn, 1. So now when you see a tall matrix and a short unknown vector, what do you want to do? There used to be only one answer. Now there's two answers. Humor me. There's only least squares, right? We want to do least squares. What are we going to do? So Gauss did not have access to IPython, but we're going to pretend that he did. And try and look at this. So what I have here is, again, we have just writing out least squares. And let's say we're given a set of points or observations. So let's say I have some observations of the planet. The observations that he had were obviously not exactly perfectly points along the ellipse, right? As you can see, like, there's no way an exact ellipse is going to fit through this because there's noise, right? In the readings, in the recordings that were being done, obviously there's going to be some kind of error. But if you have these, is this big enough to read? Yeah, so basically there's some noise that is polluting the points. And now again, here what I'm writing here is I'm just basically stacking up all of the x1 squares, then the x1 y1s, then the y1 squares, so on and so forth, to make this A matrix. My B is just a column of ones, and then I'm going to call these squares on AB. Whoops. Oh, A did not get run. Yeah. And now I can pull out these coefficients, which gives me that. I can now draw this. And now I can just basically plug these back into the equation for an ellipse, which is what I'm doing here, to get the following. Right? This is the estimated path of the ellipse. And so basically after the planet had passed through here, you can use this to when, if you wanted to predict now where the ellipse would be, or where the planet would be at a time point here, where would you predict? Right? You're going to predict along this blue curve over here. You have partial observations along the ellipse, and you want to predict where the planet or the path is around here. And that's given exactly by the curve of the ellipse. So are there any questions about this? There's these two demos, right? So we're going from something that was done back in the 1800s to something that is applied, in stock markets, basically every day today. And it's not that these are just two applications, right? You'll see a bunch of different applications to, for example, biological sciences, to social sciences on the homework, and many, many different ways in which you can actually apply this algorithm. I'll take a last question, but if not, I will see you next week.
About the null space of A versus the null space of A transpose.